Okay.
At the end, maybe.
All right. So thank you for coming. It's networking security. So announcement. This Sunday is going to be our last general meeting of the semester. So to kind of keep things chill, we're just doing a hot chocolate social. So feel free to show up and we'll have hot chocolate. It'll be in CS 1404. Forgot to put that down. So we'll have the big screen. So if you guys want, we can do like a movie, we can do Jackbox, we can do Switch games, you know, whatever you guys find fun. Okay, so this is the meeting flag. There should be a category called networking security somewhere on the CTFD. So if you find the meeting flag challenge, please do not throw sausage pizza away. Does anyone know what a flag is at? Nobody? Okay. Well, that is it's like an acronym to help you remember the OSI model names. So P is for physical, D is for data, N is for network, T for transport, S for session, P for presentation, A for application. Yeah, and then there's your daily XKCD as well.
As mandatory.
The slides are also on the CMS or on the website, so you can go and view the slides if you want to. Okay, so very broadly, what is networking? Just so we're all on the same page. So it's a way for, in the context of networking and cybersecurity, we're talking about computers sending information to each other. And the internet is only one example of a network, right? So you can have different networks like ATM networks, which aren't connected to the internet. And so, and then you can also have subnetworks attached to a main network, right? So the University Illinois net is an example of a subnetwork, or it's kind of its own internal network, but it's also connected to the internet through some parts. So that kind of makes it a subnetwork as well. And we kind of have protocols for everything when it comes to networking, because you have different devices, from different manufacturers. You kind of need some sort of protocol so that way they can talk to each other, right? Some sort of standardized language, right? As a result, there's a lot of different protocols because people like coming up with their own things to make things more efficient or more niche or specific use case. So there are a lot of protocols. There are a lot of acronyms as a result of this. The main way you want to view networking in general is through the OSI model, or there's also a more basic reduced version of this. But the idea is that you can break most computer network traffic into 7 different layers. And so each packet that is sent on a network will contain some or all of these layers, but you'll always start with layer 1 and work your way up to layer 7. And if you want to think about it, it's kind of like Russian nesting dolls, where you have layer 1 as the outside encapsulating doll, and then you could have multiple layers on the inside. So these are those layers, right? So we have, as I mentioned earlier, we have the acronym PDNTSPA. The lowest layer you can get, right? If you want to send data from one computer to another, you have to send actual physical bits, right? So the physical layer is relating to, well, this is wrong. So Ethernet in terms of like the actual Ethernet cables, fiber optics, binary, that's the actual physical layer. The data link layer is how devices know where to get from, it's basically like figuring out how packets can get from one node to another node in a graph, right? So every node in the network will have a MAC address, and that MAC address is like a sort of not technically unique, but within the network it's supposed to be unique address that traffic can be sent to. So this data link layer allows basically traffic to traverse your network. The network layer, which kind of feels like a redundant name, but this is where you have the ability to send those packets within larger distances across networks even. So this is where you see the internet protocol most commonly being used, right? And that allows you to send arbitrarily, I want to send a packet from my computer to a computer over there. And I don't really care how it gets there, right?
Yeah.
So as I mentioned earlier, layers don't care about the layer beneath it. So as long as the packet gets from destination A to destination B, it doesn't care what other nodes it traverses through to get to its destination. And then the transport layer, TCP and UDP, to kind of allow applications to build on top of that network layer, and they also provide guarantees that messages are sent are sort of, or not guarantees that messages sent will have certain properties. And then the layers 5 to 7 can kind of just be grouped together, which is why they're all highlighted blue. And this is where you'll see protocols that will add encryption, or if they're not adding encryption, it's just HTTP, right? And yeah, so the application data that you're sending to different programs don't care about how it traverses your network. It only cares that the program gets the message. Yeah.
Great. So going a little more, yeah, Nikhil.
Yeah, so like, looks like 2, 3, and 4 are all through with routing.
Right. So routing is actually a layer 3 device, as far
Yeah.
as I know. And routing is a way to essentially set a source and destination. Now, the routing is basically going to be done upon like layer 3, in the sense that when I have like an IP address that's currently there in source, the router will be able to acknowledge that IP address along with like the destination that it has to route it to. So it simply forwards and keeps track of that through like what we call a routing table, as to like say, if I were to have a packet that needs to go to like this guy, who do I tell? I do a lookup in that routing table and I'm able to tell that. So now, because it's a layer 3 protocol and the layers are pretty much like independent from the ones below them, the router's job is only to keep track of that mapping. So it doesn't need to know the stuff below.
Why do you,
That's the stuff.
or I guess, what, how does it help to have that, yeah, because you already have MAC addresses that are unique.
Right. So the way you can sort of think about it is that with the data link layer, that's deciding the physical path to take to a destination. So the slight issue with MAC addresses as well is they're not designed to be split up. Like if you think about a MAC address versus an IP address, right? A MAC address has a manufacturer ID for the first 3 octets, or not octets, first 3 bytes. So there isn't like room to actually do any networking or like build subnetworks in there. So IP addresses exist to allow that to happen, and then MAC addresses kind of serve the purpose of being a unique hardware identifier as opposed to being an address where you can send data traffic to, right?
Yeah.
So for example, a device can have multiple IP addresses, right? But it might be using a single networking network, right?
Yeah.
What is VLAN tagging something?
VLAN tag.
Do you want me to answer this seriously, or?
Huh?
So
Know how to answer this by saying that on a particular VLAN, you don't want to route traffic, of course, to a different logical subnet. So you want to tag the, is it Ethernet? No, it's not.
It's a data link.
Yeah, okay, so it is Ethernet.
Yeah.
It's a
so,
frame.
yeah.
Okay, yeah,
Yeah.
so then
So,
you
yeah.
want to tag the frame with a
V-
particular
yeah.
VLAN ID so that you don't, forward traffic to another logical subnet. But I don't know that for sure. You know that something?
So so VLANs have IDs, right? So you tag you put the ID inside the frame information, and when a device that's operating on layer 2 receives that, it knows that it can decide whether that packet can be sent to a certain can be switched to a certain output, right? So in the case of like, you know, the easiest way to describe VLANs is if you have different departments. So you have like maybe
Marketing and
a
accounting.
marketing and accounting department, right? You don't necessarily want the marketing department to access like financial data. So any traffics that are tagged with, the marketing VLAN ID, when a switch receives that, it's going to not send that out to any of the accounting ports, even if it's destined for it. It's not going to do it.
Yeah, VLAN tagging is a very basic way to implement a form of segmentation at like layer 2. So that's kind of the main purpose of it. But
Any more questions?
yeah, feel free to ask.
Akil, do you have a question?
No, I'm cooking.
Yeah. All right. So now going a little more into layer 4 protocols, which are your transport layers. The two most common ones that you will see are going to be TCP and UDP. Now, in order to really easily tell the difference, let's say that you want to simply call someone. Now, if you want to set up a TCP connection, doing TCP would be like, say, starting a normal conversation. So first what will happen is that A will send a request to B saying, hello, I am A and I would like to talk to you. That's essentially some way that you will start a connection in TCP. Now, if B is able to receive that connection, B will answer like you would in a normal conversation. B will say, hello, A, I am B, currently talking. And then that essentially tells A that B has received the request, as far as the TCP analogy here goes. Now, after that has been established, A can go and forward any conversation that he wants to tell B with anything. So now it goes back into A over to B. So this is essentially the way TCP handles starting its connections. Now, UDP does not need to have such a handshake. UDP is simply forwarding data. So doing something with UDP would be like, say, sending a voicemail out. So in this case, A would go to B without any warning saying, hey, we've been trying to reach you about your car's extended warranty, or say your information. Now, UDP does not care whether or not B actually recognizes the data, and it's just a single forward direction. So with UDP, there is no guarantee or way to know that your request has been sent because it's only sending them outward via the stream. So that's one way you could tell the difference between
Now, in UDP, you can actually still, send like the B can still send a response to A, right?
Yes.
And A, like you could use that to basically do a two-way handshake instead, so that A knows that B got the message, right? TCP also, this handshake happens automatically for any application that's using TCP. So you always know that the connection is established before you start sending your application data. So that's the key difference between UDP. So with UDP, you can just send your application data right away, whereas with TCP, it's kind of like an extra check to make sure, hey, is the server that I'm connecting to alive? And if it is, then I can start sending data. So to kind of simplify, or to kind of formalize this previous A to B, B to A to B, that is a three-way handshake. So the technical term for those types of messages are a SYN, which is synchronize, and then the SYN ACK, which is synchronize acknowledge, and then ACK for acknowledge. So Once these 3 messages have successfully sent, then you can start sending data to each other without worrying about package dropping. I this is actually not really
True.
this is not really relevant. I don't know what this is here, honestly.
Yeah.
This is inaccurate.
Yeah, not
This is when because I made these slides a long time ago, so don't listen to that. TCP does not necessarily mean it's more secure than UDP.
yeah, go ahead, Jake.
But why is that not?
Well, I mean, it's kind of the same because the security of an application kind of depends on the layers that are above what TCP and UDP are, right? So you have like layer 5 and layer 5 being session, right? So that actually authenticates a user or application data. Or you can even have presentation where there's cryptography, right? So the idea is that the medium, TCP and UDP and IP and data link should sort of be considered as the mediums for which network data transfers to. And I wouldn't necessarily consider that as one being more secure than the other. It might help, but
Yeah, and the other thing to also note is that the established connection, while it is required, the actual individuals being responsible for the connection are not set in stone by TCP. So anyone can establish a connection with anyone, which is another thing to also consider.
Well, I guess,
This is a very basic protocol.
at least this, to me, it seems like there's at least some advantage there, because in UDP you can just spoof the like IP address, right?
well, you can do the same in TCP as well.
Not really, but
Yeah, you can.
Well, I guess you need to guess the correct, like, yeah, you need to guess the correct sequence numbers, but like that I wouldn't really call that like that isn't really intended for security, as we've seen sort of. I guess it does have some security properties, but like it's not something I would really rely on, right? And at the end of the day, if I'm like it depends on your use case, right? Like I could send application message over like a serial line instead of using TCP or UDP. So the only so this might be more secure in the sense of like protocols to choose for that specific layer. But if you're building application protocols and traffic above that, do not like take that at face value, because this is just I don't know,
It's a very basic guarantee because it's supposed to work at levels above, but you also have to think about the level that's above if you're like declaring something secure. And again, like standards also matter. So that's like something to consider.
what we're trying to say is basically just because you pick TCP doesn't mean you should make your application less secure. Okay, and then UDP constantly streams data. So this has better applications where you need low latency, right? You don't want to have the overhead of the additional 3-way handshake. So it's good for like video streaming, which is why sometimes, when you're receiving a video, you see it sort of kind of glitch out, right? And the reason is maybe because there's packet drop on the way, and because UDP doesn't guarantee that the receiver receives that, then it, because it's streaming in real time, it just kind of glitches out. If you had video streaming over TCP, right, what you probably have is a lot of buffering, because you'd have, the video data getting lost in the way. And then now the client has to wait for TCP to retry and retransmit the data so it can, replay the video.
Yeah, so as you have a lot of retransmissions going on with like TCP, that's basically saying that I want to keep establishing that I'll be trying the same packets going in and out again, so it interrupts the stream. So as a result, you will get. Whereas with UDP, you'll just see a small skip because the stream would still continue. I don't have to retransmit UDP. Yeah.
What about RT?
Is just what is RTB? in
We're
the
talking
context?
about streaming. I'm pretty sure RTP is like the
Oh, okay.
streaming. protocol.
Right. Well, okay, that's an application protocol built on top of UDP.
Yeah,
I believe so.
yeah, I'm pretty sure RTP does use UDP in the background. We could look this up.
Okay, RTP typically runs over UDP.
Yeah,
Yeah. Right. So RTP is an example of a video streaming protocol built on top of UDP.
Me when QoS platinum gold.
So now that we kind of have a more general understanding of how networking works, we want to talk about some networking attacks. Not Minute because we don't have those slides prepared. But there are some pretty other interesting attacks. So the first one, which has kind of fallen out of any relevance because modern programming is good now for network stacks. But a SYN flood, as we mentioned earlier, so a SYN packet is the first packet that's sent at the start of a TCP handshake. So basically, the attacker is kind of exploiting how the three-way handshake works to basically do a denial of service attack against a server. So if the attacker sends a SYN packet to the server, right, the server sees that and then responds with a SYN ACK because it's establishing the connection. But in order for the three-way handshake to complete, the client also needs to send another acknowledgement, right? So the server will kind of wait for that handshake to finish, right? But if the attacker never sends it, then okay, sure. I guess something happened with the other client, so I'll just wait a little bit longer and see if it finishes the connection. And if not, then I'll close out the connection, right? And that's fine and all, but like what happens if you have a lot of people spamming SYN packets to the server at the same time, right? And they never finish a connection. They always send a SYN packet and then they never respond back with an ACK. So basically what would happen is that servers would start to handle all these connections, right? It would start to queue all these connections and it would never receive the acknowledged response. And because the server has all these network sockets open, it doesn't have maybe not enough memory to open up a new network socket, or also because at this point, it's kind of overwhelmed. And the kind of dangerous thing about this attack too is that you didn't even really need like a botnet to perform this attack, because you could just send many connections from the same device to perform this attack, and it would essentially take down a server. So yeah, and then eventually what happens is, the server will have to start dropping connections and then legitimate traffic can't connect, which is a problem. So the way that this problem was fixed is using a feature called SYN cookies, which basically says if I don't receive the SYN ACK, or if I receive a SYN from this IP, right, I'm going to remember that. And if it sends me another SYN, then I know that it's basically a cookie. Like I've seen this IP before establishing a connection, and I currently have a connection that hasn't been established yet. So I'm just going to forget about that connection request. So by doing that, you essentially limit connections to one time, unless you can have multiple connections at the same time, but the connection has to be fully established, right?
as like an
Yeah.
has to receive. The other thing is that doing a SYN flood, as you can like tell, is pretty guns blazing as far as like attacks go. So if you were on like some sort of like forensic side and you were seeing like a lot of SYN requests being made at like a checkpoint for like a really small amount of time, it also raises a lot of suspicions. So
Yeah.
it's not really used in practice as far as like taking down a server goes.
Yeah, because you could just block that single IP address, call it a day. Most modern firewalls, like SYN floods are not remotely applicable to the real world anymore, but they're still interesting to talk about because they're exploiting the functionality of the TCP stack. And then the other thing is ARP cache poisoning. So this is an attack that works on layer 2. So ARP is the address resolution protocol. Basically, it translates IP addresses to MAC addresses. So if I want to send data to if I want to send basically data to an IP address, I need to know like what MAC address to put my packet as, and the nearest the nearest ARP resolver will say, here, you can send the packet to this MAC address, and it will arrive at the other system. So the way ARP cache poisoning works is that your device is constantly sending ARP requests to figure out where IP addresses are and where it should send, which MAC address it should send those packets to. So one way that ARP cache poisoning works is that you kind of beat the ARP resolver's response and say, and before it's able to reply to the requester, you immediately say, hey, I am 1234, and this is the MAC address that you can use to send data. And it's actually the attacker's MAC address. So now data can flow through the attacker because the client now thinks that, oh, I can send packets for 1234 to this MAC address. And so that kind of allows you to manipulate how data is sent through a network, or how the way that packets are traversed through a network, right? And this is still pretty relevant, mostly because again, layer 2 is not meant to provide any security guarantees. It's simply a medium for traffic to send to traverse through. And so that kind of leads us to the idea of the man-in-the-middle attack, right? Where you have some entity that's running on a node sitting in between network traffic passing between two other nodes. So you can have a passive man in the middle, which is their goal is to read data as it comes through, and maybe spy on the information that's being sent. Or you can have active, where you modify the packet and retransmit it in the hopes of manipulating the responses. So any entity that's kind of in between you and your destination can sort of be considered a man in the middle, right? Because they're handling the data that's passing through. So just a quick visualization of how man in the middle works, right? So let's say you had a direct connection from A to B. Using something like ARP cache poisoning, you can trick A into sending its data link packets to the man in the middle, and then you can forward them to B or not. But the idea is that you have now inserted yourself in the middle of the network traffic. And revisiting the OSI model, you can kind of see how there's different attacks at different layers, right? So again, we talked about ARP cache poisoning. Another layer 2 attack is where you spoof a MAC address. So you pretend you either modify your device's MAC address to pretend that you're a different MAC address. This attack is actually pretty cool because a lot of basically network network firewalls will use something called MAC address whitelisting in order to ensure that only a specific device, when attached to a network, can send traffic on it, right? So if you attach, like if I was, visiting Purdue and I plugged in my computer into their network, right? Maybe my MAC address isn't whitelisted on Purdue's network, so it won't let me access produce resources, right? But maybe if I'm a Purdue student and if I have, my MAC address registered in their table, then now I can send traffic to their resources. So if I knew somebody else's MAC address at Purdue, then I could spoof my computer to basically trick them into letting me in. This is actually sort of, yeah, ARP is there. So you got DDoS and floods. Application, right? So that's where most of, CTF challenges are. You got web, phone. Cryptography would usually be in the presentation layer. And the reason we call this presentation is because the way you actually you present the data in a packet is different from how the application actually receives that data. So cryptography is an example of this. You encrypt your packets. So on a network, you can't see the application layer of data. But when the application actually receives it, it gets decrypted and is presented in that way. So that's why it's called presentation layer. It's kind of a goofy name, but yeah. Does anyone have any questions about more of this OSI model stuff? Okay. So now a very useful tool that pretty much everyone in the industry related to networking uses, not even security related, is Wireshark. Basically, it's a tool that captures all network packets being sent to your device or to some monitoring device that you may have. And you can analyze packets to see all the different information being sent in the packets and at each layer. So this is kind of what the interface looks like. And this top part is this packet list. So you can see all the packets being sent at what time to what IP. Since this is ARP is actually a layer 3/layer 2 protocol, but because ARP doesn't, people that are sending ARP messages don't know what the IP addresses are. They're actually showing us MAC addresses instead. And here you can click on a specific packet and you can see information about that packet. So you can kind of see the OSI model here. You've got frame, which is physical, Ethernet, which is layer 2, data link, IP, which is network 3, user data protocol, which is transport. You got session, which is 5, and then that was kind of it. But there will be like HTTP here at the bottom for if it was HTTP traffic. And then you can also inspect the raw packet bytes if that makes you happy. And very useful, you can use a filter. So that way you can find only packets matching a specific IP maybe. Or you can filter for only UDP traffic or only web traffic. So for example, you can just type HTTP and boom, it only shows you HTTP traffic now. Or you can filter by a specific IP address. It'll only show you IPs that match that, packets which have that IP address. And you can also, again, because TCP and UDP are basically kind of streams of data, so you can follow a specific stream of data by clicking on the packet, and it'll show you all packets related to that conversation, which is useful if you have a lot of different connections in a single packet.
Yeah, in the real world, this is also really useful for understanding communications, say through exfiltration or other methods of like sharing data. For example, a really common thing that I was able to, how many people were here for that? Yeah, so it is possible to also share a lot of data hidden within certain sessions. So one thing you could do to be able to like say follow that stream is to just hit TCP follow. And then you could see everything related to say that conversation or data exfiltration to be able to recognize these things. So it's really useful for forensics. That's something I want to mention.
And then Wireshark is a GUI by default, but its CLI counterpart is TCP dump. And then there's also a tool called Tshark, which
Is Wireshark but worse?
well
It also runs on the terminal.
well yeah, it runs on the terminal, which is why it's useful, but it's you can use it in bash scripts, or if you don't want to wait for the Wireshark GUI to load, it is technically faster. PyShark is also a very useful library because it's essentially Tshark, but it lets you use it in Python scripts, so that's kind of nice, and it has some nice APIs. We're not going to tell you.
Go to network. Net chat.
Well, okay.
You could do Scapy.
That's first meeting goal.
Escaping.
Okay. So there's some challenges. Almost all of the challenges that we have are going to use Wireshark. So you'll need to install Wireshark or any one of these other tools, but recommend using Wireshark just because it's easier to get started. And all the challenges should be solvable, or not all of them, but some of them. So there's layers 1 to 7 challenge, which is basically like kind of asking you to find information at each of the different layers. So it kind of gets you familiar with Wireshark and how to interpret network data. There's the file transfer challenge, which is basically you have FTP data traffic data, and FTP is file transfer protocol. So in this case, FTP is sending data, sending a file over the network. And FTP doesn't have any real presentation layer, which means it's not encrypted. So you can sort of find that information using Wireshark and its tools. I forgot what pool was, but you'll have fun with it.
That's a SMB force.
Okay,
So
SMB
you look
reverse.
at Hydra traffic and you figure out which one's successful.
Right, I did this right. Yeah. Okay. So yeah, it's been a while since I made these challenges.
Wait, that's not
Mm.
over.
Well, yeah, there was something
I
like
mean,
that.
that's like a
Okay.
classic.
But
Yeah.
okay,
Yeah.
yeah.
This was also tunnel vision, but slightly different.
Yeah.
DNS.
Live stream fail is extracting a video stream. So this is slightly challenging because, well, I mean, it was challenging at the time because I don't think Wireshark had the proper decoders for it, but it might now. For which one? Live stream fail. Ooh, whoopsie. I'll fix that. And then 2B2T, which was my
The oldest anarchy.
which was my a challenge I made for UACT of 2021, and that is basically you have sort of a Minecraft clone, which is mine test, but and there's traffic, and you have to figure out what it does. But
That one's fucking painful.
yeah, it is painful. And you know, that is painful, and I will also say that Mindtest provides the actual packet dissector for Wireshark. So application data is kind of hard, application traffic is kind of hard to reverse engineer if you don't have references or documentation, and all you have is the client and the server, and you have to interpret the traffic in between. Or if you don't even have that, right, and you're just looking at traffic, you're kind of trying to make meaning of a bunch of bytes. So, and 2B2T, Mindtest is relatively well documented network-wise. So the fact that this is kind of difficult, kind of helps you get into reverse engineering network traffic protocols as well. Yeah, again, next meeting this Sunday is our last meeting of the semester, and we'll do hot chocolate and sister or Holly movie or games. And it'll be in CS 14.4. Thank you.
You guys go over Wi-Fi hacking at all?
No, we
No?
didn't.
Okay.
That would
So
be cool.
yeah, so Wi-Fi, if anyone is curious, would fall under the data link layer. Right, so that is, maybe I'll go back a few slides. So or more, sorry, not data links, right? It would be physical, right? Because that is the physical media.
It ends up being a couple, it's not.
Yeah, it's,
Yeah.
But it's mainly one.
Wi-Fi is its own thing, bro. Well, it ties into, like, you have to do things whether you're grabbing the four-way handshake and then cracking it, or you're doing DOF, like, how do you classify that's kind of.
It's a lot of layers.
right, so the important thing with Wi-Fi is that, those like, it like does a lot of, like, layers that, a lot of things that could be classified in these other layers. But it's important to note that it's still all encapsulated in layer one. Because at the end of the day, it doesn't matter, like, your application data is not going to matter whether you use Wi-Fi or not. Or whether you use MAC addresses doesn't depend on whether you use Wi-Fi or not. So Wi-Fi falls under the physical layer technically, but it's very complicated.
Yeah.
Because you have, authentication to network and things like that.
Even like actual like physics behind it, like antenna.
Right.
So there's a lot.
I was talking about the classic stuff, like rogue AP, like the fact that you can GAuth unauthenticated by default still. Yeah, you can like.
Yeah.
Like if we were talking wireless transmission from a purely physical data layer standpoint, right, it would just be, an antenna to an antenna. The Wi-Fi will include things like, authentication with a radius server, which is, something that would be an application, right? So, yeah. Wi-Fi is.
Wi-Fi is
You,
yeah, another.
very tricky, but it is really fun because I do a lab once where you do, notice SSL stripping, also data poisoning, it's like files and transfer that would have been encrypted, so I could pull everything with it. Yeah. Unfortunately, of course, that's how good anymore, but it was good when I did it.
Yeah.
Also, by the way, all the installs for the drivers for this are like 10 years out of date, so for now, there's compatibility issues, but this thing has the ability to just do that. Just do that. I want to message you this stuff.
Yeah.
So I'm trying to fix it.
Do that, and then
It's fine. Yes.
About sandboxes.
This is still a thing. Remember, like, this was more the zeitgeist around